We are recording. Hi, Campbell. Had to be consistent, you know. Toby has some news to share as well. All right. We are continuing. So if we recall this photoelectric effect that we've been working on for a couple of lessons now, today we're going to look at that simulation again. We can grab the laptops out if we want so that you guys can tinker with it yourself. As I said last lesson, though, I did find out that simulation is a bit broken. They had to convert it from Flash so that it would still work after we stopped supporting Flash, and it broke in that conversion. It doesn't work properly right now, but you still sort of get some of the ideas from it, so it's still. Now, what I prompted you guys to start thinking about last time was this variable voltage and why we need a variable voltage in this circuit at all. This photocell, and that's what we call it, a photocell, a cell where photons can interact with electrons. That photocell acts as a battery. Quite literally, it has a cathode and an anode, which is what batteries use to generate a potential difference, generally through some electrolytic liquid, which is just like an electron liquid. So it does the exact same thing. It just does it slightly differently by shining light on it. We can eject those electrons, they get attracted to that anode, and we create a current flow. Now, the voltage that we impose on that other cell is called the stopping voltage. And as I said, the reason it's so useful is if we can get the current to drop to zero by imposing a reverse voltage, when we hit that zero current, we have induced a voltage that is exactly equal but opposite to the voltage being generated by the photocell, which is great because otherwise we wouldn't know what the voltage is in the photocell, okay? So that's one way of checking what your photocell's voltage is actually generating. And that's, I'm sure you can imagine how applicable that is to industrial use, but also when they were originally doing the experiments here, it was very interesting to see kinetic energy, because they knew how to calculate kinetic energy. Remember the formula we learned about kinetic energy of an electron the other day? What's it related to? Who can remind me what formula we used to find the kinetic energy of the ejected electrons? Not this formula, obviously. There's another one. No, yeah, so that does work, sorry, but that's not, there's actually three, I guess. H. Right, the kinetic energy is the difference between the photon's energy, purely you calculate the photon's energy in joules using HF, and you take away the work function of that metal. So experimentally speaking, they had to go and investigate the work functions of the metals, prove that metals, let's say they used lithium, right? And they proved that lithium happens to have this as its work function. They could then calculate the electron's energy based off how it was ejected, based off the light they used. They could calculate the electron's kinetic energy, and they measured the voltage and found that the kinetic energy and the voltage were proportional, and the constant of proportionality, the thing we had to multiply by, was just the charge of an electron. Pretty clean and simple, right? Now, of course, it didn't exactly go in that order. Things were sort of happening all over the place and it all sort of came together, and once again, SI units was a change in units to sort of make everything work nice and neat. But it does now work nice and neatly. And to find the voltage generated by a photocell, all you need to know is the energy of the electron, charge of an electron. Charge of an electron is constant, so we already know it. Can you please copy that down into your books? Alrighty. So let's break those graphs down a little bit, guys. Thank you, everyone. Hopefully it's clear. Hopefully it's clear what the idea behind stopping voltage is. So this VS, you might also see it called cutoff voltage. V naught, some people will call it. So voltage is now zero, the net voltage is zero. Little things like that. But the idea is always the same. We are inducing a voltage in our photocell, and then reversing that voltage using some actual power source, some sort of power pack or something, to cancel it out. So we're creating, in both situations, a voltage which induces a current, and if we oppose the direction of those currents, we can actually cancel out the effects of the voltages, right? Essentially, any ejected electrons will make it to the anode and then just sort of stay there and have nowhere else to go because there's a reversed voltage imposing a current facing them. And as I've established, that kinetic energy is exactly proportional to that, just multiplied by the charge of the electron, which is pretty straightforward. That's pretty cool. These graphs are meant to be from Leonard's, I don't know if they're from Leonard's original experiment, but there's a couple of really interesting things about these. Okay, first thing, we already get this, right? As current increase, or realistically, as you increase frequency, current does not change. You're increasing the energy of the individual electrons. And this is what our simulation the other day failed to show. It was actually glitching out a little bit, and you guys will remember that there were still electrons coming across at zero, at zero current and stuff like that. But realistically, when there is basically no current, you can start increasing your threshold frequency where all of a sudden there is a set current. Increasing your frequency further does not increase current, but it does increase what? In the electrons. Their kinetic energy. Charge is constant. So as we then increase the energy of our photons by increasing their frequency, getting smaller wavelength photons, ultraviolets or, ultraviolets or gamma or X-rays or something, really small wavelength light with high frequencies and high energies, we don't change current. Current does not increase. Can someone remind me why? What property of photons did this sort of proved it? That graph proved that photons happen to do this thing. What was it? Yeah, you're on the right track. It's not more photons, it's just higher energy photons. And because we've established that the collisions must be one-on-one from this, a single photon interacting with a single atom ejects a single electron no matter what. If it's a higher energy photon, the whole photon is absorbed by that atom and ejects an electron. That electron just has more energy. Now, electrons, while they do have sort of a wavelength and a frequency to them in some sense, talk about that later, they get an increased energy in kinetic energy. So they actually move faster. Light travels at the speed of light, so it can't have a different amount of kinetic energy. It can only have a different amount of internal energy in terms of frequency. Okay? Any questions about that graph? That's what we spoke about before with threshold frequency and that sort of stuff. Is that okay? Ask questions if you have them. Okay? All right. This is different. Who can tell me something just from observing this? Look at your y-axis is microamps. Your x-axis is voltage. Notice that the x-axis goes into negatives. Your current doesn't really go negative, although you can talk about a negative direction on current. Doesn't really matter, doesn't really make sense. We're talking about the negative voltage. Now this is to be very clear here, this is not the voltage overall in the circuit. This is the voltage being induced by our power pack, okay? So when we induce no voltage, have a look at the current being generated. Now notice the difference between these two lines. This is a dim light, this is a bright light. The difference between a low intensity light and a high intensity light is what? The amount of ejected electrons. More intense light just means more photons. Doesn't mean higher energy photons. It does mean higher current. So more photons, more ejected electrons, a higher current measured. Higher energy photons, not an increase in current. Our simulation failed to show that clearly the other day. That is the findings of Leonard's photocell experiment. What happens down here? And maybe someone can point out something that's kind of substantial about this side of that graph, because there's something pretty fascinating. Max? Yeah, and at the same what? Well, they've reached the same, yeah, they're at the same voltage, and that produces the same current. And what current is that? Right, so we call this the stopping voltage, or you can see here they've used the C, VC, cutoff voltage, same thing. What's really fascinating is it's the same for the bright light and the dim light. It does not matter if you have more intense light. The voltage is the same. Go back into your brains, remind me, what does that voltage relate to? Or just look on the board, it's right there. Kinetic energy. So it doesn't matter how intense your light is, you're not going to give them more or less kinetic energy. Originally, when they conducted this experiment, that wasn't clear because there was a higher current. But they found out that the voltage you induce is the same. The voltage induced by the light, regardless of its intensity, was the same. The amount of potential difference, or the velocity we could get those electrons to, the force with which we could accelerate those electrons, was the same for a bright light or a dim light. We just ejected more of them if we had a brighter light. So the cutoff voltage is the same no matter what our intensity is. That was the key finding from this. Okay? And that meant that kinetic energy and voltage are purely related through the frequency of light, the energy of that light, not the quantity of photons. Kind of cool? I'm going to give you guys some check your learning questions now, and that's pretty much us done. If you want to, while you're doing the check your learning, you can grab out a laptop and go to that simulation. I think it's still in the G drive folder, I believe. That's where I put it originally, wasn't it? Oh no, I just did it on the board. I can chuck it in the G drive and you guys can look at that if you like. But otherwise, we are done. Here is your questions. This is a tricky one, and I'd encourage you to have a conversation with the person next to you, and maybe even jot down a few of the summary points that are relevant to this discussion. So what was the classical physics? And what would we expect if classical physics was actually describing the photoelectric effect? So classical physics includes the electromagnetic radiation proposal, but basically before quanta, before the idea that these were discrete packets of energy, we used to think that light was a continuous energy wave. When you switch on a light or when you look at the sun, it's just waves of energy with certain amplitudes and magnitudes of energy. And there was just an infinite sort of continuous number of them. It wasn't, you couldn't count it, right? You could measure how much energy there was, but you couldn't say, oh, there's 6 waves coming at us. Say that the wave had an amplitude of 3 meters tall or something like that, like you can with oceans, right? But you couldn't, like sound. Hard to quantify sound. Of course, we now know that you could. But it is for light. Have a think about what that might look like. And your other question. Do they look the same size? If you'd like to play with that simulation, guys, go grab a laptop, get it fired up. I'll pop the link in the drive. Just be careful. I think it is probably going to glitch out on your computers too. I think it is because of how they ported it from Flash to whatever they're using now.